Welcome back to ECE 220. We are now back to worrying about equivalence, but we may get complex at the end, I'm not sure. But last time we talked about complex numbers and how they can be used for sinusoidal analysis, and that's important for lab number 2. Now we're going back to try to finish up in the next few lectures Chapter 4, and that will then take us through the Thevenin and Norton equivalence, maximum power transfer, and superposition. That's the plan for the next few periods. Today, Group B, Section I, has their lab. Don't forget that to attend. You also have a homework assignment due, and Group A has a couple of things due this week. Tomorrow, I can't keep track of the days, but tomorrow is Wednesday. Everyone in Group A has to submit their lab report for lab number 1. And on Saturday, that same set of sections needs to submit or upload their pre-lab into D2L. I've also been told to remind you that if you are in electrical and computer engineering, you need to apply for advanced standing if you are in that position, and that is a narrow window of time that you can apply for that. You might check your emails, open them up, read them, and see what you need to do. You need to go find our undergraduate advisor and speak to Alexis about what is required for advanced standing, and I think she sent you something yesterday with that information as far as some pointers on advanced standing or what that involves. Today we want to get into methods 2 and 3 of finding Thevenin and Norton equivalence. The last time we used the direct method, and now we want to use a couple of different strategies that work in or with different scenarios, or some are more effectively applied in certain situations. The second method is to deactivate the sources and find your R Thevenin that way, and then you find V Thevenin or I short circuit as we typically do. And the third method is the test source method, and that's the one that you apply if all you have in your circuit are dependent sources. The test source method, you can apply either a current test source or a voltage test source, and that will hopefully make more sense as we go through. Then we have all of these different examples, and maybe given time we'll get into complex impedances and show why you need to be able to perform complex manipulations or be able to do complex algebra if we now have our resistors being impedances, which means that now they are generalized resistors or they are now complex quantities. How do we play with those? How do we combine those to obtain, let's say, a Z Thevenin, a Thevenin impedance, instead of now, or that's a generalization of what we've been doing, which is this R Thevenin or a Thevenin resistance. Summarizing, what we have done before is the direct method of finding a Thevenin and Norton equivalent circuit for a mix of interconnected circuit elements that could contain resistors, independent sources, dependent sources, but we want to know what does this circuit look like equivalently between two terminals, A and B. In the direct method, we had 3 steps, and the first 2 actually are using a modified interconnected circuit that you start with. Meaning, let me see if I can say over here that In step number 1, as sort of a refresh, what do we need to do to the circuit terminals A and B, when we are trying to find the open circuit voltage, or Thevenin? What do we need to do to those terminals A and B? Do we do anything with them? The circuit with terminals AB opened, shorted, put a elephant between A and B. What do we do between A and B when we're trying to find V open circuit? Hint, hint. In the V open circuit, we leave A and B open circuited, don't we, in step 1. That's the configuration of our circuit for step number 1, is we have the circuit with terminals open. Contrast that with step 2. Now we modify the circuit to find I short circuit, and now we short those two terminals A and B. Once we've computed Thevenin and I short circuit, then we can take their ratio, V over I, and find the Thevenin resistance, R Thevenin. That's step 3. If you now have a scenario where you are confronted with a circuit that doesn't have any independent sources, there's nothing you're going to see relative to terminals A and B. If there's nothing energizing the circuit, you won't see anything across those terminals, and consequently you won't be able to apply this direct method. So we need alternatives. The second method, and we'll go through an example of this shortly, is the method that we call Deactivate Sources. In this method, we set all the independent sources to 0. And we need to be comfortable with that. If we had voltage sources, we replace those with a wire. If we have current sources, we open those up. And now we try to find our Thevenin under those conditions. We look at terminal A and B, and what's the resistance between those two terminals? That's what we did on the exam. Can you now start reducing this network of resistors down to one resistor between A and B? That's what step 1 does in the Deactivate Source method. In step 2, we simply find either Thevenin, our open circuit voltage, or I Norton, or the I short circuit current, to find the next parameter that we need in addition to our Thevenin. This particular strategy works best when we have independent sources and resistors. Finally, one more method, which is referred to as the test source method. We first deactivate all the independent sources. Then we apply some test instrument between A and B. That test instrument could be supplying a current of 1 amp, or it could be applying a voltage of 1 volt. Once we've done that, let's say we apply a 1 volt test voltage source. Then we measure or calculate IT, and then we can compute our Thevenin from that test source relationship or condition. Our Thevenin is now VT over IT. If we had applied a test current, IT would be 1, and we would calculate what VT is and take that over IT to obtain our Thevenin. All we've done then so far is find our Thevenin. We still need to find the source in that Thevenin or Norton equivalent. And then step 3 is to find that with all of our independent sources reactivated or active. This one always works. Method 3 always works. So if you go, I don't know which one to use this one. It's a little bit more involved maybe, and sometimes you feel a little uncomfortable doing it, but method 3 always works no matter what kind of circuit you're trying to apply it to, and you have to use this when you only have dependent sources in your circuit. Let's now look at applying these two new methods that we've introduced. Method 2. So now on an exam, I'm not going to probably tell you what method to use. You'll have to decide, do I use method 1, method 2, or method 3? And it's going to depend on maybe the way you're feeling that day, or the circuit, or a combination. But method 2, now I'm telling you, let's try method 2 for this particular circuit. And when you're looking at these to find Thevenin equivalence between terminals A and B, what you sort of want to do is step back and say, okay, what is in this circuit? Is it simply resistors? Well, then I'm just going to find a resistor equivalent. Or do I have independent sources? Do I have dependent sources? What do I have? And that's going to help inform your decision as to what you do in terms of the strategy that you apply to find the Thevenin equivalent. Here, we don't have any dependent sources. So this one's sort of set up to use method 2. And this gives us an excuse to play with deactivating sources. If we now deactivate the voltage source, we only have one independent source, and it's a voltage source. What is involved when we deactivate that source? We simply short out the voltage source, and if we do that, what do we end up with? Now we have a circuit with the following values. Those haven't changed. All we've done is now replaced the voltage source with a wire. Now can we find our Thevenin looking into terminals A and B? And if it doesn't look like what you want it to look like, you could bend 25 around and say, oh, that's in fact parallel with the 100 ohm resistor, if you don't see that immediately. You can distort, you can grow and shrink these wires however you want to make them look like you want them to look. So now we have 25 in parallel with 100. And we've done this one enough to realize that that boils down, well, it's giving us a resistance that's less than either of the two, which you better get, and it's a nice number. It's now 20. And now hopefully you can see that our Thevenin is what value between terminals A and B? 30 ohms. It's the series combination of that 20 with 10. So now we have our Thevenin. The next step is to find Thevenin, which now we have to reactivate the independent sources and find the open circuit voltage between terminals A and B. What can you see or appreciate by looking at this ask? We're asking to find the voltage across terminals A and B. Is that voltage appearing anywhere else in the circuit? Or how do we find VOC? Or can I make the following statement? The open circuit voltage, VOC, is the voltage across the 100 ohm resistor. Why can I make that statement? Why is that true? Does the 10 ohm resistor affect it? If you now start doing KVL around that sort of, you're seeing a mesh maybe on the right hand side, you have, if we went counterclockwise, we'd go minus VOC plus 10. What's the current through that 10 ohm resistor? 0. Plus 100 times the current through that 100 ohm resistor. So in fact, this current, let's say I sub 0, is equal to 0, and that's why we can say that VOC is the voltage dropped across that 100 ohm resistor. If that's the case, now we can apply KVL over here. Let's say that's capital I. Now we have minus 200 plus 25I plus 100I is equal to 0. Or we now have 125I equaling 200. Or we now have 8/5 of an amp flowing through that left mesh, or 1.667 amps. That current we can now use to find the voltage dropped across that 100 ohm. The only current flowing through that is the capital I. And we could back that out if we wanted to, but let's just say now that by performing another KVL that we just did, but we can actually say that VOC now from our earlier argument is 100I. One of the reasons I didn't divide that out, now I have this being 160 volts. And that is the Thevenin voltage. I now have the Thevenin resistance from step 1, 30 ohms. I have the Thevenin voltage from the second step. Now I have my Thevenin equivalent between terminals A and B. R Thevenin is now 30 ohms and V Thevenin is 160 volts. We didn't have to find I short circuit current. We simply found R Thevenin and then we found V open circuit. And that now led us to this Thevenin equivalent. Let's look at method 3, the test source method. And I'm sure you all just remember this particular circuit. we analyze this circuit with the direct method. We now have a way to test our work if we want to. So if you go back a couple of lectures prior, you should find the Thevenin equivalent that we obtained for this particular circuit. Now we're going to use a different strategy to find that same Thevenin equivalent. So you don't have to just use one method to solve these particular problems. With the test source method, the very first thing that we do is deactivate all of our independent sources. So looking at this, we didn't have to really decide which method to use, since I told you we were going to use method 3. But now looking at this, you see you have an independent source, you have a dependent source, and you have some resistors. So that's sort of saying you need to use methods 1 or 3. Let's use method 3. And when we deactivate all of our independent sources, if I had a voltage source, what does that look like? What does the red arrow imply? What do I do between those two terminals if I had voltage sources? I just short those terminals. If I now had a current source, so this is now everywhere that I had an independent, you don't mess with the dependent sources. You leave those in place. You can only deactivate the independent sources. The voltage source is short and the current sources open up. If there was then a branch, now you can remove that branch where that current source existed in your circuit when you're doing this first step in method number 3, which is requiring the deactivation of our independent sources. The next thing we do is we apply a test source to terminals A and B, and we have the choice. We can either apply a 1 amp test source. That means then that our denominator is going to be 1. We would calculate the voltage across that source, that 1 amp source, and use that in our numerator expression for our Thevenin, and that would give us our Thevenin. For the 1 volt source, now we have the 1 volt in the numerator. We compute the current coming out of that test source and use that in our denominator, and that would give us our Thevenin. So either of these we can use. Sometimes it's maybe more convenient to use one versus another, but you should find the same result by using either one. So now if we go back to what we started with, here is our source. And maybe before we, well, how do we now deactivate or unenergize this circuit? What do we need to do? Or what does that circuit look like? We identify our independent sources. Now we have these nodes to worry about. Do we need any other nodes to be concerned with if we're worried about our independent sources? And what do we do between those two nodes now in this circuit? Now we need to short that out. And this is now our unenergized circuit. And I think you can see now over here we could combine that 25 ohm resistor with the 100 ohm resistor and collapse that down to a 20. And now we have that 20 ohm in series with 10, and we still haven't disturbed I sub x. We've retained I sub x. even by collapsing those two resistors. We need to retain I sub x, that dependent variable, because we have a dependent source. What we don't yet, or what we haven't yet decided, is what we want to do over here. What do we want to put inside the source? A current or a voltage? We can either apply a 1 amp or a 1 volt test source, and that's the decision that you have to decide or make. But before we go there, let me just remind you what this test source, or does this even make sense? Or have we seen this before? And now I want to let you know that you've been using that test source in the lab. You've been measuring resistance with your ohm meter. An ohm meter is really a test source to allow you to measure the resistance across two terminals. So now it's time for art class. Now let's draw. Now I'm really nervous. My hands are sweating. I'm not the artist, but let's do an aside. So here the aside is the test source method. Although this may seem a little bit weird, really we're just pulling out, in a sense, like a digital multimeter. So the test source method imitates how an ohm meter works. Meaning, if I now had an unenergized circuit, sitting here, and I had two terminals, A and B. And here in my lab, I have this ohm meter. And that's now going to, essentially, now I connect this with leads, and I can now, the ohm meter is effectively, it has a battery in it. Now it's going to apply a voltage across those leads, and it's going to sense what the current is, and then it can now display or provide this ratio VT over IT, and that's now your resistance relative to terminals A and B in this unenergized circuit. So the test source method is not that foreign to us. Let's now go back. So now we have this circuit where we've combined the 20 and the 10, and this current was a dependent variable I sub x. Then we had 20 ohms here. And we had our dependent voltage source, which was 30 I sub x. And now what do we want to do? Well, what can we do? If I made this a 1 volt test source, does that already kind of tell me what's going on at A? That fixes the voltage at A. And that now I can write a Kcl equation at that, and then I will be able to measure or compute this current I sub t. So what's Kcl at A? Capital A. And sometimes that I sub x just gets in the way. Sometimes I might think, okay, I want to know that current, and that current relative to terminal A, and IT, capital IT, I'm going to leave alone. So IT is coming in, and these blue currents are going out. The current going to the left, can I find an expression for that? What is that current going from right to left out of A, capital A? That's my test voltage, 1 divided by 30. So now I have 1 over 30. What's the vertical current? Blue going down. It's where I am, 1, minus the voltage where I'm going, which is 30I sub x. Now I have to kind of keep track of that. So I have 1 minus 30I sub x over the resistance between those two locations. Those two currents going out are equal to the current going in, which is I, capital T. I could find capital I, capital T if I knew I sub x. But we can compute I sub x. That's just Ohm's law. Or we could say, well, if this is now what I'm considering to be my reference, this is now 0 volts. Here's where I am, 0 volts, minus where I'm going, which is capital A. That's 1 volt divided by 30. That's the current I sub x. I sub x is now 0 minus 1 over 30. I now have an expression for I sub x. I can plug that in to my original Kcl equation. I have 1 over 30 plus 1 minus 30 times minus 1 over 30 over 20 is equal to I sub t. Or this now gives me 2 over 20 plus 1 over 30. If I get a common denominator of 60, is that okay? (8 over 60) or 2 over 15 for IT. Wow, I'm running out of room. All because of art class. They didn't have this in art class. I couldn't grow my paper when I was taking walks or doing whatever I was doing in my art class. One story. So I was in art class and they go, the art teacher, she goes, oh, go for a walk. She goes, draw it on your paper. So I go, okay, I go out of my front door, I go down this sidewalk, and then I go here, and then I go down this street. She walks over and she goes, what are you doing? I go, I'm going for a walk. She goes, no, look at some of the others. And they're, doing all of this. And then we were supposed to color it in or shade it in. Needless to say, I'm an engineer, not an artist. I don't know what my grade was for that exercise. Where were we? We were trying to find I sub t. Why? Why did we want I sub t? Why did we compute I sub t? What was the point of that? We were trying to find that because we knew what the voltage was. We know this. That's 1. And RT, the Thevenin resistance, is now VT over IT. Or this is 1 over, and what did I say this was? Is this 2 over 15? So this is now 2 over 15, or 7.5 ohms. And as I said before, the next step in this method 3 is to find either V Thevenin or I short circuit. We've already done that from an earlier lecture. We computed V Thevenin in this to be 100 volts for that circuit. So now we can actually sketch our Thevenin equivalent. And that, analyzing that, if we're attaching different loads to terminals A and B, you can analyze it with this circuit, or you could go back and say, oh, let me put something across terminal A and B and keep analyzing that circuit. We've now condensed that circuit to the left of terminals A and B into something that looks maybe a little cleaner to play with. Do you want me to go through what would have happened if I did a 1 amp source? No? Okay. Me neither. So let's go on. But you could. You could do that tonight and find out if your R Thevenin is the same. Let's look at this example to finding the Thevenin equivalent. Threes are wild in this circuit. We have a lot of resistors, and they all seem to have the same value of 3 ohms. We now want to find the Thevenin equivalent between nodes A and B. What can we start to appreciate about this particular circuit? We might start looking at it and saying, okay, do we have any independent sources? So now we've raised a flag, haven't we? Can we do the first strategy, method 1? I didn't tell you what method we were going to use. Method 1, we need V open circuit and we need I short circuit. What's V open circuit? What's the voltage across A and B? Is there any energy in this circuit? No, there's a dependent source and there's no independent source. The voltage across AB is 0. So we now need to use what method? Method 2's out. Method 1's out. What method? Maybe method 3. We only have 3 and we just removed 1 and 2. This has no independent sources. And it's really a circuit with resistors with a dependent source. So now if we use method 3 and we just found or reasoned what was our open circuit voltage? Is it energized? Is this source energized, or is this circuit energized? No, V open circuit is 0. So our Thevenin voltage in this particular circuit is 0. What we're looking for now is some resistance between A and B with this dependent source. So now let's apply a test source. Which one? How many test sources do we have? We could apply, so I guess our exams are multiple choice, so that wouldn't get us any extra credit, would it? Or partial credit by drawing that, but you're starting to go in the right direction. You're putting an independent source between A and B. What do we put in the circle? Well, you could either put an arrow or a plus and minus sign. We're using either a 1 amp or a 1 volt. And depending on what we put in there, how are we going to analyze the circuit? Gosh. What are the analysis strategies that we've developed? If you used a current source, so here's our thought process. If we said, okay, here's a current source, well, that's kind of begging us to, if we did all of this, if we see 3 window panes or 3 meshes, now this particular mesh is given. And we have 2 unknown variables to solve, mesh 1 and mesh 2. Correct? So that would say we have 2 variables unknown that we would have to solve. 2 equations and 2 unknowns is what we would be looking for. Let's see what the other one provides. What if this was a 1 volt test source? Now what would we do? And let's just go ahead and make this our reference node. Now what do we have? Well, now we start looking at nodal analysis. So we're really saying MCA, mesh current analysis, or node voltage analysis. That's what we're working through now. We have these nodes, essential nodes, that are not the reference node. We have 3 of those. Oh, great. But one of them is determined. It's given. That's the 1 volt. That's the one closest, or that's at little a. What about the other 2? Well, if we called this, let's say V1, and this V2. But V2 is 4I sub x. And we can find I sub x in terms of V sub 1. So here we really just have the one unknown node voltage, V1, and one constraint equation, which is given by I sub x. So that might be easier. We can kind of work with one unknown and one constraint equation. So let's now apply this test voltage. And if that's what we're doing, we just said we are going to do node voltage analysis with V1 and one constraint equation. What's the constraint equation? one of the relationships is that v sub 2 is 4I sub x. But we really want our constraint equation to be giving us information about that dependent variable I sub x. So this one I'm not even really, I sort of discounted this one, but you do need to know that. That is one relationship we need to kind of keep known. But do we know I sub x in terms of the other node voltage? Isn't I sub x the current, the vertical current, which is V1 over 3? Now we know V sub 2 is 4 V1 over 3. So the only unknown we have is V1 in all of this. Let's now find V1 by Kcl there. Let's write a Kcl equation at the V1 node. So we have this current, we have that current, and we have that current. The current going to the left is V1 minus V2 over 3. Let me just be sort of very descriptive. And we know what V2 is. We're trying to find V1. Down, let's forget I sub x. That's just another variable. We don't need it. We just need V1 equation. The current going down is V1 over 3. The current going to the right is V1 minus where we're going, and where are we going? What's the voltage where we're going? 1 divided by 3. And those sum to 0. And what did we say? Well, let's just multiply this by 3. That'll clean that up a little bit, get rid of some of the fractions. We have V1 minus V2 plus V1 plus V1 minus 1 is equal to 0. And we said V2 was what? 4I sub x, and I sub x was V1 over 3. Now we have an equation that has all these V1s and a constant. We can put that on the other side. So we have 3 minus 4/3 V1 is equal to 1. Or that's now 5/3. Or V1 is now 0.6 volts. And what is now I sub x if we need it? I sub x was this 4/3 V1. Did I do that right? Just seeing if you guys... What in the world am I doing? Why am I having such a hard time? What did I want? I sub x? Oh! Thank you. If you weren't here early, I got here about an hour early. I thought this was Wednesday or Monday, so I'm out of it. I sub x is V1 over 3. Is that what I kept hearing communicated to me? And V1 is now 3/5, so we divide that. So this is now 1/5. Where were we going? We now wanted to find IT. IT was now Oh, can be found from that. IT is coming in here. And what's going in or going out, we could now say, let's worry about everything going out. And we can now say that IT, now we're doing KCL again. IT is equal to 1 minus V1 over 3 plus 1 minus V sub 2 over 3. And if you go through all of that, you'll end up with this being 0.2 amps. So quickly, we now have our Thevenin. Our Thevenin is VT over IT, 1 over 0.2, or 1/5, or our resistance is now 5 ohms. And that's now our Thevenin resistance looking into terminals A, B in that particular problem. We'll pick up with maximum power transfer next time.